Today we're going to run this charged rod question. It is question number 6 in chapter 23 of the book that I was talking about earlier in this channel. And we are going to copy this guy. You could see over here on the side it says QC. I think this means quantitative and question, quantitative and calculate or something like that. But I do know this S means symbolic, meaning the answer is not going to be a number. It's going to be something with symbols like KE, Q, X, Y, R, maybe symbols like this. Yeah, I have this. Oh, here it is. Qualitative / conceptual and symbolic. So this is from the book, somewhere in the first chapter or somewhere in the beginning of the book, like in the content section. Alrighty, let's do this pretty quick because I got something to do soon. So what we're looking for is a uniform charged rod of length L and total charge Q, same as last video, except now we are looking for the electric field at this point here, a distance D above the left side of the rod. And they give you this picture here where they set it up at the origin with the rod at the x-axis and the point on the y-axis, a distance P up. Find the components of the electric field at the point P on the y-axis of a distance, a distance D from the origin. What are the approximate values of the field components when D is much greater than L? So this part of the problem is telling you something very important. Find the components of the electric field. It's asking you to break apart the entire electric field into components. So something in the x hat direction and something in the y hat direction. Now this is very important because it's actually how you're going to solve the problem. So let's take a look at this problem here. Let's draw a coordinate system like this. X, Y. We got the point P over here, which is located at 0 on the x-axis and D on the y-axis. This is what symbolic means. They have this symbol D. D could be anything. Later, actually, we're going to send this D to a very large number. Like imagine this distance D was like 10 million meters or infinity, and we're going to see what happens. But we also have the rod over here. So I'm going to put this guy like this. All right. Let's put it here in the center, make that aesthetically pleasing. All right, let's take these lines here and imagine a little DQ, okay? This is a DQ. If you remember, the charge over some unit length, or in this case, we could use X as the length, is going to give us the linear charge density of the rod. Density. Hopefully that's visible. Let's put this right here. And in this case, what this equals to is, well, we have charge, which is Q, capital Q over L. So we have this relationship here. Let's keep that in mind. And now let's imagine we have an electric field, which will be given to us by this equation here, KE, integral of a small charge element dq over r squared. That electric field will be pointing like this. So let's say we draw a line connecting this charge element dq to the point, and it's going to create this component dE. I'm calling it dE because it's created by a small dq. If you want, you can put dE over here, and you just got to remove this integral because when you're not integrating, that dq doesn't remove, and it creates a small dE. Doesn't matter too much, but let's say that this is the component that this part of the rod creates. If we look at a component here, this will do a similar thing. So we can add all these guys up and we will get some other maybe dE2, right? And you can see all of these will come from the rod like that, and we can combine all of them together to get the total electric field. Now the cool thing is we can break apart these guys into their components. So let's say I take this and I draw a small dotted line like that. That will be the x component, so dEx. And we can take the y component, which we can draw like this. Or we could draw it over here. It doesn't matter, it is the same length. That here will give us the y component. All right, looks good. Okay, so let's do a little bit of analysis here. We want to calculate these guys. We want to calculate Ex and Ey. And how we get these is we use the same equation, Ke, Coulomb's constant. We have a dq here and an r squared. Integral dq here and an r squared. The only thing that's missing is this is the equation for the total electric field. Here we're looking for the x component, and this also is the equation for the total electric field. Here we're looking for the y component. So we want to break down these equations somehow, and here's how we're going to do it. Take a look at the geometry we have here. We got the rod, which is a length L. So this position here is L on the x-axis, x equals L. This distance here is D, right? It is given to us. And these two things create a right angle triangle like that, right? We have the triangle like this. Now, with good old Pythagoras, we can find the hypotenuse of this. It'll be, let's call it R, which is square root of D squared plus L squared, right? You guys could do Pythagorean theorem. So we have that as well. And let's also label this side theta. So that's not given to us in the problem, but using SOHCAHTOA, sine equals opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to adjacent over opposite. For a general right angle triangle like this, if we have theta here, the opposite side of theta is this leg here. The adjacent side of theta is this leg here. And the long side is always the hypotenuse. So using this thing here, we can create an equation to calculate theta because we have all the sides of the triangle. So you can use either one of these. You can use sine, cosine, or tangent. Let's use sine because it is the first one. So we write sine of theta, right? The trigonometry functions always eat some angle. In this case, we labeled it theta. You can label it anything you want. Phi, you can label it x. Normally, it's convention to use theta. And we look at our little mnemonic. So sine equals opposite over hypotenuse. In the triangle that we have here, we actually calculated everything. So in this case, the opposite side is this D and the hypotenuse is R, which R was not given to us, but it was calculated using Pythagorean's theorem. Right, so you may be like, okay, how is this going to help us solve the problem? It's good to label some geometries, and this theta actually is going to be crucial. And the reason it's crucial is because, well, the goal here is to break apart a vector, right? Let's say this is the total electric field, E tot, into its components. So we want to break down this component. This is the Ex. And this is the EY. How we do that is we have an angle here and we can use this and these identities to break it down. So I'm gonna literally write it here because I can kind of remember what these are, but I'll show you how to get them. So you have the total electric field multiplied by cosine, it gives you the Ex component, and the total electric field times sine gives you the Ey component. If the angle we had here, this theta, was actually given to us here, then this sine would be a cosine, because in this case, the opposite is on this side and the adjacent is on this side. You see what I mean? Basically, just write out the triangle like this and use this to calculate the components. So how I found these guys was I said, okay, let's pull out one of the bad boys. We'll use sine. Actually, let's do it both at the same time. We'll use cosine as well. You can use tangent, and we'll use tangent over here to just show you guys what is going on here. But remember the mnemonics? SOHCAHTOA, hypotenuse, opposite, adjacent. These are all the letters that are being used here. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is adjacent over opposite. So a tangent is the one that does not use the hypotenuse. And that's why tangent is not used when determining components of a vector, because E total is the hypotenuse of the vector, of the triangle, sorry. I hope that made sense, but let's take a look at this. Sine is opposite over adjacent. So opposite in this case of our triangle, with theta being here, is EY. EY. Sorry, I said sine is opposite over adjacent. I meant sine is opposite over hypotenuse. Remember your little SOHCAHTOA acronym, or mnemonic. So we have opposite of this angle theta is EY, the EY component, and the hypotenuse is the total electric field. You see how if you had this angle phi here, the opposite side would be the EX field. So in that case, this sign goes with the EX. But in our case, we had the classic triangle where the theta is given in the bottom corner. So sine will go with the Y component because the opposite side of this triangle is the Y component. I hope that makes sense and I'm not speaking too fast. I just have to dip out by the end of the hour. So I'm going to try to finish this problem pretty quickly. Let's do cosine. Cosine is adjacent side over hypotenuse. In our triangle, the adjacent side is EX over E total. And for funsies, let's do the tangent. Tangent is adjacent over opposite. In this case, adjacent is EX and opposite is EY. So let's multiply this by E total on both sides. E total. This E total cancels with this E total, and this gives us an equation for EY. On the other side, we have E total times the trig term, which is sine theta. So this gives us one component. We'll do the same thing on this side, multiply both sides by E total, which gives us the X component as the total electric field vector times cosine of theta. And in this case, we can multiply, I guess, both sides by EY, and we will get that EX is equal to tangent theta. Let me write it the same way as the other guys. And here we multiply EY. So this one is not too much used. It's used if you want to find the angle theta here, and you're only given the X and the Y legs. So you can do tangent theta is equal to opposite, in this case will be Y for this triangle, over X. And then if you have both of these, you can find this ratio and you can take tan inverse of both sides. And then you will get a value for theta. Theta is equal to tan inverse Y over X. Not too important, but let's use what I showed you guys here onto these two equations. So what I'm going to do here, since it's getting a bit messy, I'm going to grab this, copy that, and place it right here. So since we now know that, take a look at this. We have this dE, which is the total electric field vector. It's technically this. And we want to get this dEx, the X component. We also want to get this dEy, the Y component, which is here. And what we've created using our geometry is, take a look with this laser pointer. I showed you that this triangle over here, we can label it as D. We can create this using Pythagorean's theorem. And we have this length, which is L. I labeled this angle theta. And from that, from the triangle here, I can calculate this theta and I can actually get a value. You can actually use this equation here. So theta is equal to tangent inverse Y divided by X. In this case, Y is the opposite side over adjacent side. But you can take anything. You can take sine of theta is equal to opposite over hypotenuse. You can take cosine of theta is equal to adjacent over hypotenuse. Any one of these equations, set it up here with the legs of your specific triangle, and you can get a value for theta. Let's actually calculate it. Let's use sine theta is equal to, in this case, the opposite side is D. The adjacent side is square root D squared L squared. Let's take sine inverse on both sides. sine inverse of sine theta. And this equals to sine inverse of this entire thing. So d squared plus L squared square root, put a d there. Boom, this sine inverse cancels with this, and this gives us an equation for theta, which is sine inverse of square root of d squared plus L squared. Okay, so this is the actual value for theta. Now, if you take a look at this, right, what we have here is one triangle drawn like that. That is the triangle of our setup. And over here, I've drawn the electric field vector coming out and kind of following this hypotenuse line, right? This is E total. This is the component of the electric field created by this portion of the wire. So what I want to do here is decompose this guy into its components. So in this case, I will have this as the EX component, this as the EY component. Remember, I have theta here. And if you kind of know your similar triangles, that will also give us this theta here. I mean, let's just think about it. We have one line, it's a straight line going like this. And we have one line here, it is horizontal. One line here, which is horizontal. This horizontal line is the same as the horizontal line creating the bottom side of our triangle. And this horizontal line is the same horizontal line creating the EX component. So this will give us the same angle here and here, theta, theta. So if we have this theta, technically what we can do is do the same thing that I showed you there and create the equations E subscript X is equal to E total. In this case, the triangle we have here, the opposite side is EY, right? The opposite side of this is EY. And the adjacent side of that theta is EX. So adjacent goes with cosine theta. And we have an equation here for EX. You could take EY, the same thing. In this case, it is the opposite side, opposite over hypotenuse. So we use sine theta. So technically what you can do to these equations here is, since this is the E total, in order to get this equation here, we just need to model it like this, which means just multiply it by cosine theta. Here we have EY, this is the E total, this entire integral, that's the definition of E total. That we could just multiply by sine theta, and that gives us the components. So let's just quickly rewrite that here. KE integral of dq. Remember, we haven't done anything to this integral. This is just the general definition of the total electric field. But since we want to find the x component only, we multiply the total electric field by cosine theta because of all this geometry kind of mumbo jumbo that I did here. I hope that makes sense for y'all. We're going to do the same thing for this component, r squared sine theta. Now here's where it gets crazy, guys. We have an equation for r squared and we have an equation for sine theta. You can replace these. And how we're going to replace them is, remember, r squared technically is this distance here from the component dq to the point in question, P, where we're trying to find the electric field. I already found the distance r over here using Pythagorean's theorem. So if we take r squared, that is literally just equal to the standard form of Pythagorean's theorem, which is d squared plus L squared. It's just the triangle, right? And well, d will never change, but as we change along the x-axis, the length L, then that length will change. So technically what we should do is replace this with an x. Do you guys see what I mean? We're not going to take the component where x is equal to L. We're going to instead take x at any location along this wire. It's kind of like the previous problem. Whoops. Let's take this. We're going to start here, right? X is equal to L, and then we're going to sweep the integral all the way across the wire, the bar, or the rod. And we're going to create a different triangle for each value of x. So technically, this equation r here, we can rewrite it as d squared plus x squared. I'm just calling x the variable that we're going to integrate over here. So I hope that makes sense. And what we can say with these equations is ke is a constant. It's always going to stay the same. dq, I don't really know what to do with it yet. We're going to leave it as is. R squared, I just told you, was d squared plus x squared, not L squared, because L is a constant. We want to use the variable x, which is going to be the thing that we sweep across and integrate over. I know you see a dq here, but we're going to change that in just a second, since you might feel like this dq is like the variable of integration. I mean, I actually did speak about it a little bit earlier. I brought up this thing here. I'll copy that so you can see the linear charge density is going to be brought into play over here. And you can see how we changed this little L over here into an X, or technically a little dx. A small part of the charge divided by a small part of the wire will give me the linear charge density. So technically a dx times a lambda will give me dq. I just multiplied both sides by dx in this equation. So this will be a very nice thing. And actually, we can replace this dq by exactly that, lambda dx. We made a variable change using this equation here, and we changed the variable of integration to dx. I hope that makes sense. And remember, we also have cosine of theta here. Now we can do the same thing on both sides of the equation here. We have lambda dx. This is going to apply on this component as well. And we have d squared plus x squared, which is going to be the r squared. And then we have this sine of theta. Now remember how we actually define sine of theta. We have this SOHCAHTOA. And if you look at our original problem, this is theta, this is the opposite side, this is the hypotenuse, and this is the adjacent side. The adjacent side in this case will be x, okay? Because as we change the triangle, so let's say we have the rod over here and the point D over here, and we're going to have some point dx, right? As we're taking this dx, first we start over here where dx is equal to L, the length of the wire. And that creates this triangle. We have the triangle here with one leg the size of D, one leg the size of X, which in this case is L, and then the hypotenuse, right? Now, if I take this dx, and I'm going to take this as well, and I sweep it across here, let's say I stop and I sweep it here, then I'm going to create this new triangle. So one side of the leg is again going to be D. The other side is now going to be this new distance. And we're going to have this new triangle here. But theta is still going to be the angle here. Before that, theta was this angle here. So you can see why we're using an integral here. Because as we're sweeping across the rod and we're taking into consideration each of these dq's, there's dq's everywhere here, we are using a different dx, okay? So let's take a look at what the theta or the sine theta and cosine theta is going to equal to. So we can decompose that and get rid of theta, because theta is a variable we want to get rid of. We want to replace everything into this x here. X is going to be the variable of integration. So how we can do that is look at the triangle and use this identity, which you guys have remembered using the SOHCAHTOA. Sine of theta is equal to opposite over hypotenuse. In this case, the opposite side of theta is always going to be the same thing. It's going to be D. That's never going to change. And then hypotenuse is going to be square root of D squared plus X squared, right? We changed it from L because X is the variable that we're going to sweep across the bottom side of the rod. We can do the same thing for this, not sine. We want to calculate cosine. And the reason we're calculating these is, again, to get rid of this variable theta, right? You can see now I have this identity for sine of theta in terms of D and X squared. And in this integral, I also have things in D and X squared. So it's looking nice. We're getting rid of variables, which is kind of what we want to do when we want to integrate something. So cosine theta is adjacent over hypotenuse. We're going to do the adjacent side, which in this case is X. Remember, we are calling the bottom side of this triangle X, not L, because as we sweep across, it changes from L to some variable X. X is the variable, right? I don't know what it is. That's why it is a variable. So we're going to throw in the hypotenuse, which again is d squared plus x squared, and then take a square root on that. Cool. Now let's take this, and let's also take this, and let's copy that, paste it over here very quickly, throw these guys down here. This is how we've changed both of our integrals. If you look at the first rod problem, we didn't do this with the x and y components because the rod had a bit of symmetry. We only had to do the x component. In another scenario where we find the electric field at a point D right above the center of the rod, we also don't have to do this breaking apart of components because there's a symmetry to the problem. I know it might be a little confusing which problem to use which technique, but this is why you work out the problems on your own. You take a look at how it's done, and after a while you kind of get a inkling of how to solve these problems. So actually I can kind of see a simplification we can make here. This lambda is just being multiplied in the numerator, and it is a constant, so we can pull that bad boy out. And you actually can see that in the previous electric field of a charged rod video as well. So now what we have is d squared plus x squared dx. We're going to replace this cosine theta by this thing here. Don't use opposite over hypotenuse. That is literally not involved in the problem anywhere. This is just the mnemonic, the SOHCAHTOA thing. Replace it with this because this is actually talking about our problem. It is using components from our rod. So what we have here is, I'm going to put this in brackets and change this square root to a power of 1/2. And I'm just doing that for a bit of simplicity. You guys will also see a bit later how that will be helpful. So we have a d squared plus x squared 1/2. That is in the denominator. In the numerator, we have x, and that integral looks pretty solid. If you want, you can replace this dx over here with this x, but it really doesn't matter. Like, you know, both of the things on the numerator are being multiplied. Plus, we're going to simplify the integral in just a second. So this one, for the y component, we have d squared plus x squared. On the numerator, we have dx because we pulled out the lambda. In this case, we are multiplying by sine theta here. That is d squared plus x squared in the denominator. In the numerator, we have just d, no x. You see the difference between these two? That's also a different integral that we're going to do. So now that we have this, let's simplify the integrals just a little bit more. The ex is looking like this. Ke lambda, these are constants, we're leaving that out. And take a look at this. This thing over here is d squared, which is the distance. Don't confuse this d with this d. That is a silly mistake to do. D squared plus x squared in the denominator. We have d squared plus x squared here, except it's power 1/2. So if you remember from exponents, and also there's a multiplication sign here. So if you remember, you could have these things like a to the power of x times a to the power of y, and this will give you a to the power of x plus y. So if x and y are like 2 and 3, then this will be a to the power of 2 plus 3, which is, whoops. What is 2 plus 3, guys? I'm kind of forgetting. 5. And you can double check this. A squared is a times a, and you multiply by a cubed, which is a times a times a. This will give you 1, 2, 3, 4, 5 a's, a to the 5th power. Makes sense? That is pretty nice, and it also works with fractions. So in this case, what our a is d squared plus x squared. That is a to the power of 1. And we're multiplying by something, a to the power of 1/2. So this will be a to the 1 plus 1/2, which is equal to 1 is the same thing as 2 over 2. And when you add that to 1/2, the denominator stays the same, and 2 plus 1 is 3. So 3 over 2. So I hope that made sense. In the numerator, we have x times dx, right? Because we have x over here, we have dx over here. In the denominator, what we have is the whole thing, d squared plus x squared, close brackets, 3 over 2. Now check this out. This is the completed integral. This is where you need to get to in this class. I know I did it kind of quick, but if you can get to this, no need to worry about how to solve this integral. It's going to be given to you. So I hope that made sense. Before we solve that integral, let's do the same thing to the y. So we're going to copy down ke times lambda because that is where our integral was last left on. In the denominator, we have the same thing. So we have d squared plus x squared, which is 3 over 2. In the numerator, we have d times dx. And the cool thing is, this d is actually a constant because it does not depend on x. If you remember what d was from all the way at the top, it's the distance that is above the rod where we're trying to find the electric field. So to simplify the integral a bit more, you can put this d out here, and then you can put this dx right over here, right? Okay, guys, check this out. This is golden. This is where you want to be at. These two integrals, once you solve them, you get the components of the electric field, and the problem is solved. So I'm sorry I'm kind of going pretty quick. I have to leave in about 10 minutes, but let's see if I can solve these. Just so if you're sitting on a test and you actually aren't giving the answer to this integral, maybe you have an idea of what to do. And I think I can actually solve one of these on my own. So this one here, we have d squared plus x squared. This is 3 on 2. And we have an x dx here. So what I can see is I can take this bottom thing as u. U is equal to d squared plus x squared. And if I take du, a derivative on both sides, remember that this d is a constant. So when we take a derivative of a constant, it is 0. But when we take a derivative of this x, it is a variable. So take a derivative of x squared, the 2 comes down, the x stays, and then we also have a dx here. So to simplify this, we have du is equal to 2x dx. Okay? And now you can actually simplify this integral using u sub, which is the first kind of trick you learn when you learn calculus. And oh, I forgot the bounds on all of these, so that is actually a big no-no. Well, okay, let's look back real quick. The variable of integration is dx on both of these, so you know the bounds here are going to be x lower and x upper. What are these bounds? It's, well, the lower one is going to be when x is the smallest. So remember when I told you that we're going to take this rod, dq, and we're going to start here, calculate the electric field created by this dq, and then sweep it across this entire integral? It doesn't really matter which direction. You can start over here at x equals 0 and sweep all the way to x equals L, or you can start at x equals 0 and sweep all the way down to x equals 0. This is the entire thing contributing to the electric field in this section. And conventionally, it is good to use the lower bound as the smaller number and the upper bound as the bigger number. So we have x is equal to 0 at the lower bound and x is equal to L at the upper bound. And I think that is the correct bounds. So these integrals are actually the ones that you're going to use. Sorry about that little mishap there. Now, when we're at this stage, we've replaced the denominator here by u 3 over 2. And in the numerator, there's this x, right? And we can replace this x, but first, let's replace this dx. So dx, I have an equation for it here. Let's divide both sides by this 2x. So we're going to move 2x on this side. 1 over 2x du is equal to dx. So now we can replace this entire thing, 1 over 2x, inside of this integral and replace the dx. So we have du here. We have the x from the original thing, right? I'm going to keep that there. But from the u substitution, we also have this 2x in the denominator, right? And this is the cool thing with u sub. These x's actually cancel, and it makes this integral possible to do. So this 1/2 is a constant. You can pull it out, and that simplifies the integral into this. Ke lambda over 2. The integral now is u in the top and u in the bottom, we have to replace those. But take a look at this. We've simplified this crazy integral into u3 over 2 du. This is a solvable integral. You could solve this on your own if you weren't given the solution to this entire thing. Don't worry about it. You're going to be given the solution to the entire thing. But let's also replace these bounds over here. So if you remember, we changed the variable of integration into this u over here. So in this case, we're going to have to replace also the bounds over here. So let's take a look at this bound and this bound. For the lower bound, I have x equals 0. I'm going to plug in x equals 0 here. That means u is equal to d squared. So that means the lower bound is just d squared. Pretty simple, right? The upper bound is x equals L. And if I replace x equals L here, I get d squared plus L squared. So here I get d squared plus L squared. And this is my final integral. Now I can integrate this. If you remember, this thing is, well, the actual integral, I'm going to replace the constants here. You put big square brackets like this, big square brackets like that. I'm going to put the lower bound, which is d squared, and then the upper bound, which is d squared plus L squared. And then inside the integral, we have, u to the minus 3 over 2. With an integral, first what you do is add 1 to this. So minus 3 over 2 plus 1 is minus 1 over 2, and then we divide by minus 1 over 2. I hope that made sense. If it didn't, don't worry. Just review your integrals a little bit. But basically, we can pull this 1/2 out. This 1/2 will cancel with this, and we can leave a minus sign in here. So we have ke lambda. Over here, what we have is minus 1 over the upper bound, which is square root of d squared plus L squared, minus negative 1 here, and then the lower bound is u to the minus 1/2 is just d, okay? Also remember that u to the minus 1/2 is just 1 over square root of u, okay? That's why I'm putting the square root here, and that's why I took off the square on this d. So this is actually the answer. Sorry if it looks a little messy. This is the answer. We have ke lambda, and we have this factor inside over here. You can simplify this factor. Alrighty, I am back. I'm just making a double check here that we got the correct answer. So last time I ended off with getting the EX component of the electric field of a rod, a distance d from one of its edges. The rod has length L and total charge Q. Or if you take the charge density, Q divided by total length, you get lambda. So the EX component, I did a very quick integral of it, and I hope you were able to follow along with me, but we got the answer above. So what we got here was square root d squared L squared. This was after a bit of u substitution. Here we have a minus sign. And then on the second term, we have minus and minus makes a plus, plus 1 on the top and d on the bottom. So this is the total component that we get for the EX side of things. And if you want, you can put the denominator here as a common fraction. So I guess we could do that. Doesn't hurt. Not really needed, but most of the time when you have a symbolic answer like this, it's very useful to make everything in a as compact of a notation as possible, like compact everything. So let's say I want to put everything in a common denominator. I will multiply both of the denominators. So I have d as one of the denominators and square root d squared plus L squared as the other denominator. That way I can add up both of the denominators. In the first term here, what I did was multiply by d on the bottom in order to get this. So I have to multiply d on the top in order to not change the fraction too much. So if I multiply minus 1 by d, I get minus d. On this side, I have to multiply by square root of d squared plus L squared. in order to get the top and bottom to be the same. So I get this, and since I want to have this minus d on the back, I will just put this here and this d here, and these two things should be equivalent. So I don't know if this looks better or this looks better. They both look pretty gnarly, but they should be equivalent and they should be equal to the EX component of the electric field. So now that we're done that, let's go back and see where the Y component was. And this is what we had for the Y component. We have not solved this yet. And what I did was, well, we stopped at this stage here, and I told you guys that if you're at this stage and you have solved and gotten to this and gotten to this, you should get answers for these integrals, right? This is an integral x dx with all this crazy stuff with an x squared 3 over 2 here. This is a complicated integral to solve. But I showed you guys, if you take this as u and do u substitution, this 2x for the du, it comes in here and it cancels this dx. It cancels this x. So it simplifies this integral. And this one you're actually able to solve with u substitution. In this case, you're not able to solve this with u substitution. You actually have to do a slightly more complicated maneuver. And this integral, actually, I am not sure how to do on my own. So I'll probably search it up. And if you're in a scenario where you have this on your test, you will 100% be given this integral in the back. They might put a here, 8x squared, 3 over 2. This thing, they will put in the back of the equation sheet, and they will say this is equal to something plus c. And then you can evaluate this integral as you normally would. Okay, let's copy that, paste it down here. Did I copy and paste it? Paste. Cool, we have this. Let's try to evaluate it. Oh man, so what we have is KE, all right, lambda. We pulled out a D over there. And what we want to put in here is the integral with bounds. So what is this integral? Man. Well, let's see if our original trick works. Last time I took this as u, right? So I said, I'll do the u sub here in blue. U is equal to d squared plus x squared. When we do u sub, we also have to find du. Derivative of d squared is 0 because d is a constant. It is not a variable. X, however, is a variable, so we differentiate that with respect to x. And then we also add this dx here. This is how you get the du and dx conversion. So if we divide both sides by 1 over 2x, we get du over here and dx. So we can simplify this integral using the u substitution. So now our bounds have changed from x to u, and they're actually the same ones. So we have the same equation right over here. If we plug in x is equal to 0, then u1 is equal to d squared plus x squared, which is 0. And the top side, we have the same bounds as before, so the bounds are the same. Now let's replace some stuff in the integral. We said u over here in the bottom, 3 over 2. And dx now is equal to du, and we have this 2x in the denominator. Now this is the annoying thing, this x, because well, we have to get rid of the x because we're integrating with respect to u. So how do we get rid of this dx? This x, sorry, I didn't mean to say dx. Well, we have to use this equation, which is our u sub equation. If we solve for x, we get x squared is equal to u minus d squared. And we square root this to get an answer for just x. And now we have an equation for x, and we can replace this whole thing down here. So you can actually see this integral is, it's not looking good. It's not looking good at all. Basically what we have is integral du on the top, we have u 3 over 2, and then we replace this x, we can pull out this 1/2, right? This 1/2 is a constant, pull it out. along with all these other constants here. I'm not writing it. I'm just trying to see if I can solve this integral on my own without any help from the equation sheet, but it looks like I can't. I'm not too sure what to do in this case. I have a u to the power of 3 over 2. I have a square root u here. It looks like an ugly integral. I don't like it. So what I'm gonna do is erase this. So what I showed you guys here is u sub does not work. And it does not work, and basically the integral here is going to be something a little bit more complex. Normally you pull it out and try to find an answer. In the case over here, in this integral, u sub actually did work, because when I did this, du pulled out this 2x dx, right? You can see that because we differentiate this x squared. And this 2x, once you move it to the du side, it gives me 1 over 2x. And when we multiply this whole thing by 1 over 2x, when we replace the du for the dx, it cancels out with this x here. So this x and this x cancel. And then we just have something like this, u to the du. So this integral is actually very easy to solve, and this is why u sub works sometimes. In this case, it did not work. So I'm gonna pull up integral calculator and see if I can. Let me actually just pull up a little. Boom. Let's search up integral of 1 over this. Actually, I'll do a squared. In our case, we have d, but it's okay. I'll do this squared, and then I'll do this to the power of 1 over 2. You see what I did? Basically just wrote our whole integral there. There is our integral, and we get an answer. Holy, wait a second. Oh, it's not to the power of 1 over 2. Yeah, I was confused because I did not expect an ln in there, a natural log. It's to the power of 3 over 2. Search that. Okay. All right. Check this out. So we have an answer here. So let's rewrite this. Ke lambda d, open brackets. Now let's put our integral. Here we have the integral over here in this page. 1 over open brackets a squared plus x squared. In our case, let's replace a with d. It doesn't matter. And then close brackets, 3 over 2 in the exponent and the denominator. Differentiate with respect to x. That is exactly what we have here. You can, in fact, think of this d as a constant a. It's a constant, doesn't matter. What we get is a squared, which in our case is d squared. And then we have a square root d squared plus x squared. So the answer isn't actually that crazy looking. And we have an x here in the numerator, which is an interesting thing. Here in the answer, they have a plus c, but when we're doing definite limits or definite integrals, we do not have a c because the c gets canceled out. So when you're doing homework, just search up an integral if you can't solve it. But when you're on a test, do not worry. They're going to give you this answer. The important thing is, can you actually set up the problem from here all the way using trigonometric terms, breaking stuff apart, seeing that you should break apart stuff in components, SOHCAHTOA, all that, so that you can get to the final stage here. And honestly, once you get to this, you'll pretty much get full marks if you haven't made any mistakes. So yeah, this is a physics class, not a math class. So let's get an answer for our y component of the electric field. What they're testing your knowledge on is the concepts. And let's replace now the top thing. So we have d squared in the bottom. I'm going to use 1/2 instead of a square root. 1/2 exponents. Here we have L squared, 1/2 exponents. On the numerator we have L. Put that big minus sign, this, and then we have 0. Now look at this. Since we have x in the numerator, 0 divided by anything is 0. So the second half of this is just 0. And we can simplify the integral like that. So now we get a final answer for EY. It is KE lambda d. Don't forget about all those constants following through the whole way. And here we have a big bracket, d squared plus L squared 1/2. And then here we have L. And actually, if you want, you can cancel this and this and simplify it a little bit more. So cancel this, cancel this. Let's bring this guy a bit closer. And the only reason we could have canceled that is because there is no second term here. You know, no fractions that need to be combined. It's just one term. And again, that is because the lower limit here was x equals 0. When you take the second portion of your definite integral, you plug in x equals 0 here, and x divided by anything, if x is 0 in the numerator, will give you just 0. So that helps us simplify things just a tiny bit more. And we have this over here. Cool. So let's take actually this, not the second component. We're going to copy this, and we are going to paste it here. And we're going to take the y component, and we're going to just put a red box around these guys. And I'm going to bring up the original problem that I had written over here. So, copy this. Paste. Shrink that down a little bit so we can see what's going on. And I'm just going to erase some stuff here. Erase this, erase these. Okay. Erase that. Erasing these tiny little orange boys. Erase this, and erase this. And erase that. Actually, bring that book. Let's bring that back. So what we're saying is the electric field created by a charged rod, which maybe is pointing somewhere in this direction. It has an x component, so an x component like this. It has a y component like that. And when you take this, you can get the total electric field by doing this, E squared plus EY squared, and taking the square root of these two, because it's just a triangle, right? So that is the magnitude of these guys. And also, if you remember from SOHCAHTOA before, you can actually find the angle of these by doing tan inverse of, and in this case, the angle we're looking for is this angle here. So it would actually be, well, let's first find this angle here. Adjacent over opposite. Adjacent is EX over opposite EY. And theta here would be this angle. And we are going to do, I think we're going to do 180 degrees minus this angle, right? Because technically what we want is the angle from the x-axis to here. And what angle we found was this tiny angle here. So we're going to do 180 degrees minus this tiny angle here, this theta, which you find using the trigonometric identity. But they will not ask you for this. I'm just showing you that you can find it if you wish. And also, let's erase this. Oops. Also, another part of the problem that they actually ask is, what would these equations look like if this d, this length d, was much larger than L? So how they write it is d much larger than L. So L in this case could be like 1 meter. Let's say d was 1 million meters. Million here stands for 10 to the power of 6, 1 million meters. Or let's say it's infinity, some huge number. So this is part of the problem. And by the way, this is the solution here, these two components. I hope this looks pretty comfortable. This looks kind of all right. If you want, you can switch these two since we have a minus sign here. You can remove this plus sign. You can move this all the way back here, move this here, and put this minus sign between them if you want. You know, it's up to you. But yeah, this would be the answer. And you can see how this is a bit more wonky and a bit more nasty than calculating the electric field at some point P over here. Or in another scenario, you find the point P over here, a distance, for example, distance D vertically up and a distance L over 2. So this is placed in the center, L over 2 of the rod. So the electric field right here. And the reason this is easier to calculate is because all of the horizontal components, the ones going this way, they cancel out and you just get a vertical direction. So you don't need to calculate many components. That is another problem that I'm going to do maybe later on. But I wanted to show you this one for calculating the electric field at the edge of the bar. And this would be the same electric field here or here or here. A distance D from the edge of the bar. So yeah, I want to show you guys the second part of the problem here, which is, well, first of all, let's take a look at this. Find the components of the electric field at point P on the y-axis, a distance D from the origin. So we found the components, and it is a symbolic problem. What I want to show you here is symbolic problems. Ask students to solve the problem using symbols, and that's what our solution looks like, using symbols. So what are the approximate values of the field components when D is much greater than L? Explain why you would expect this result. So let's take a look at that. D is much larger than L. Let's take these components here. Paste. The distance D now is much larger than L. Okay, let's take a look at them one at a time. I'll put them like this, all right? Let's take a look at them one at a time. Alrighty, in this case, here's how you do these problems. If D is much larger than L, then something D squared plus L squared is pretty much equal to D squared, okay? A very, very, very big number, D squared, plus a super tiny number, L squared, is pretty much equal to D squared itself. You can think about 1 million, 1, 2, 3, yeah, this number here. If you take this squared plus 1 squared, this is pretty much equal to, almost equal to, it's not exactly equal to, it's almost equal to, right? And the bigger D becomes, if this gets closer to infinity, the more true this equality becomes, right? You plug this into your calculator, plug in 1 million squared plus 1 squared, see what the number equals, and then actually plug in 1 million squared, you know, and see how close those numbers are. So we can make this kind of approximation here, and the approximation we are doing is that D squared plus L squared is approximately equal to D squared. So if we can make that approximation, then this whole denominator here, it basically just turns into D squared. And if that makes sense, then the square root of D squared is equal to just D, okay? And if you see here, we have 1D minus 1D. Here we have 0. 1 over D minus itself is equal to 0. That is the simplification we can make if D is much larger. If D is much larger than L. If and only if is what that triple letter F means. Okay, so basically what this is telling you is E in the X component is equal to 0, if this is the case. That was super easy. Now let's take a look at this scenario, EY. So again, this thing here, if D is much larger than L, then this pretty much equals D squared. This is the approximation you're making. So you can erase all of that in there. And since we have a square root over here, the square root cancels this 2, and we just get D in the bottom. And we actually have another D here. So we have D times D, which gives us D squared, okay? Looks really cool, right? And we can't simplify this anymore. So what does this equation equal? EY KE lambda. In the numerator we have L, and the denominator we have D squared. Does this look familiar? Well, if you remember lambda, it is defined as the charge over L. So if we multiply both sides by L, then we have lambda times L is equal to Q. Here we have lambda times L. So we can replace this with a Q in the numerator and D squared in the denominator. And if you remember, this D is actually the distance here. So if we go really high up, this is what D is much greater than L means. If this distance D is much larger than L, all the way, like you go all the way to the cosmos and you look down on this rod has an electric field in the y direction of this. In the x direction, it doesn't have an electric field component. So what this is saying is, let's say the rod is really tiny, it's all the way here, and the distance D is all the way up here. It is much larger than L. This is L, this is D. As you can see, the distance D is much greater than L. Then the electric field in the y direction reduces down to the electric field of a point charge. Remember, a point charge was just KEQ over R squared. In this case, R is replaced with the letter D because that is the distance from that we're measuring the electric field at. So it's very cool. Once you take this approximation of a rod, you get back the equation of a point charge. So this rod, if you go really far away and you look at it with your eye, this is your eye observing the electric field of a charged rod a really long distance away, 1 million meters away. This rod just looks like a regular positive point charge with charge Q. Isn't that cool, guys? All right, I hope that was awesome. I know these videos are like 1 hour long, guys. I'm literally Zoom speeding, like I cannot speak any faster. So reducing these problems down to a 10-minute video, like I'm still trying to figure out how to do that. So I hope this was helpful. I hope now you have an idea of how to calculate the electric field of a charged rod. Next problem we are going to do is calculating the electric field of a charged rod like this, a distance D from the center. So it is going to be a symmetric scenario here with this theta equaling this theta, or a distance L over 2 and L over 2. By the way, one final thing I want to say to you guys is, in this case, they just gave us L and Q and whatever, all these symbols, and we got this scenario here. But the cool thing about the symbolic problem-solving thing is, lambda is the charge per length of the rod. I can increase this charge to whatever I want. I can do Q, 3Q. I can set the lambda to whatever I want. This is the cool thing about a symbolic solution. I can also set this distance to whatever I want, and I can set the length of the rod to whatever I want. So solving the problem using symbols like this is super nice and nifty because you can plug in whatever answer you want, and this is a general equation for the electric field of a rod in this location. So I can now plug in whatever length of rod I want. I can put 10 kilometers here, 10 kilometer rod. I can put a negative charge density here, negative. And it would give me the answer for the electric field at this point here. That's why it's cool solving it with symbols like this. And you can also do little assumptions and approximations like this, and you can see cool things like this. The electric field of a charged rod really far away. It looks like a point charge. So I hope this was helpful. Subscribe. The 10 millionth subscriber to my channel will get a giveaway. So thank you guys, and feel free to drop a comment if you have any questions. Have a good one. Peace.